Hello everyone, welcome to EMH Math Portal, and I am Irvin M. Howard, your math tutor or EMH math tutor. Welcome again to another math session of EMH Math Portal. Is a series of videos loaded on the website, which is located at the URL address or the web address emhwebs.com, and you should be able to see it at the end of this video. What I want to introduce, the lesson will begin with square roots, and square roots primarily are numbers or non-negative real numbers, and so much that individuals who don't know what the square root is all about, I want to just spend some time to identify that and then proceed with the lesson. And I've written an example here, and as well as the definition. Now, the definition of square roots based upon Blitzer's pre-calculus book, and it's a great book. And I look at the preliminary lessons that prep the students up before proceeding with the higher level pre-calculus math. But I just want to use that as a reference to start for the beginners and use this book. And I have the reference label on the end of this video. Now, a square root is if A is a non-negative real number, the non-negative number b such that b squared equals to a, denoted by b equals to the square root of a, is the principal square root of a. All right, let's take a look at what that definition means, and then we'll use this definition to work out several problems. And I want to identify, and I'll put on a note, perfect square, so that the next time we do problems, this will be a hint on how we can find square root problems by understanding what is a perfect square. But let's look at 25, square root of 25. 25 inside the radical, this is called the radical. I'll write the word radical, all right? 25 in the radical is called the radicand, and the little shelf right here is called the root. All right, the root means that there is the number on the shelf, and that number indicates how this radicand should appear itself, or how it should not replicate itself, how it should transform itself in terms of what the number represent in 5. And this is somewhat similar to bases and exponents, and I'll kind of relate that in a few seconds. But as we look at the 25 in the radical as the radicand, the 25 is the radicand, the root in a way tells the radicand how it should make itself transform, or it goes under a type of a change. All right, I tell my students the root tells what the radicand, how it should appear in the radical. All right, so the root is 2. So we need to identify how 25 can be expressed in terms of the power. All right, now note 25. I'll just put 25 right here. 25 itself, plain 25. If we identify 25 in terms of express itself in terms of bases and exponents, we remember that 25 can be expressed as 5 squared. All right, 5 squared is the exponent if you've seen the other videos that I have, and 5 is the base. But when we talk about radicals, it's the reverse. All right, and later I'll tell you that it's the reverse. So the root recognizes how many times that this radicand can express itself. All right, so let's look at it. So if I can write the radicand in terms of exponents, all right, 25 can be expressed as 5 squared, all right? The root, in a way, cancels out the exponent, all right? And I'll explain the canceling out later, all right? The root cancels out the exponent, and this gives you 5, all right? 25 represents a perfect square, all right? That means that two numbers of the same base can be multiplied together, and you will have a perfect square. For instance, 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. They're perfect squares. Any number you multiply times itself is a perfect square. 12 times 12, 144 is a perfect square. So if I look at these numbers, square root of 144, if I can express it, the root is saying you should express yourself in terms of bases and the exponent. All right, so I have square root of 12 square, and then this exponent here, the root cancels out this exponent. So as you bring it out, the root slashes the exponent, and you have 12. All these numbers works the same way. All right. Now let's look at a little bit more of a real world relationship. You know, you have pairs of socks, right? You have 2 pairs. Everyone has 2 that makes a pair, right? Now look at the roots. Look at the square roots and radicals. All right. Let's look at 25 again. All right. So if I can express 25 in terms of what numbers, what 2 numbers, what number that I could think of that can be multiplied together, all right, the same type, all right, that will give me the 25. So when you're thinking about pairs, you think they're alike, all right? So, you know, you have 2 hands. You have only 1 pair of hands. You have 2. Just like you have gloves, you have 1 pair of gloves. That makes 2 gloves for each hand. So if we can look at finding square roots based upon the shelf here that says 2, find out what can make a pair from this number. And the numbers together have to be the same, just like your hands. You have a left and right, but you have 5 fingers, and they're alike. I'm not talking about reflection, but if you can look at it in terms of looking at the number, how many can make a pair, all right? In this case, there's 2 numbers that can make 25. If you can identify them, 5 times 5, right? All right, you identify 5 times 5. And then you can identify that 5 square makes the pair. All right, so this is just explaining in terms of exponents. This explains in terms of pair. 2 make a pair. All right, so it's 2 items that make a pair. All right. So if you look at it in terms of 5 squared, that's still the same thing as this, because, you know, when you multiply a number times a number, you're just identifying how many times you're multiplying. So you write it in terms of bases and exponents. Now, when you identify, the root says, I want you to tell me how many numbers I need to make a pair. In this case, you need 2 numbers to make a pair. In this case, 5 times 5 can be expressed as 5 squared. And then as you bring this one out, the root cancels out the exponent, and you have 5. It works the same way. It's, all right, square root of 144. All right, it says 12 times 12. All right, that's your pair. It takes 2 to make a pair, all right? And then if I explain it in terms of exponents, it's 12 square, all right? With the root, all right, if the number is not present on the shelf, it's understood to be 2. So the root tells the radicand, I want you to multiply I want you to express yourself in terms of pairs. You know, what two numbers that you can transform to make a pair. And we've identified that 12 times 12 makes one pair. So it takes two numbers to make a pair. And then as you bring this out, 12, the exponent, the root cancels the exponent, and then you have 12. And you're going to see that what I mean about the exponent is canceled by the root when we talk about rational exponents. Let's work out a few examples. Square root of 64. It's the same way. What two numbers that will give you 64? And the same two numbers have to be alike to make one pair. 8 times 8, or square root of 8 squared equals to 8. As the 8 comes out, the exponent cancels out the, it's canceled by the root. All right. Now, if you have something like this, negative 49, all right, this goes back to the first rule of square roots. If a is a non-negative number, so in the radicand is negative, so it can't be negative in a radical. The radicand can't have negative. That means that if the radicand has a negative, that's saying that what two negative numbers that will give you 49 is no such thing. It takes one negative times a positive to give you a negative number. So this does not work. In the real number system. But it will work with the complex number. When you complex numbers, when you have negative numbers in the radicand, a negative radicand, it will work with complex numbers, and negatives are recognized by the complex number of I, and we're not going to talk about that, but we'll just strictly talk about real number systems, okay? But if we have square root of 49, which is positive, it will work. So what two numbers will give you 49 that makes a pair? 7 times 7 can be expressed as 7 squared, which is 7. This comes out, as it comes out, the root cancels out the exponent. And we'll do, we'll try, let's see, let's try this one. Negative 9. Negative square root of 9. Now, since the negative is on the outside, it'll work. What two numbers will give you 9 and they make a pair? All right. 3 times 3 can be expressed as 3 squared. And as the 3 squared comes out, the root cancels out the exponent, and you have 3. Okay. And what we'll do, we'll try some other ones later that are larger numbers, which will I'll utilize the product rule to help you identify the numbers as perfect squares. Now, these numbers, all right, all of them represent perfect square. All right, perfect squares. That means that any two numbers that you can multiply in the radicand, the same two numbers you multiply in the radicand, the same two numbers that you multiply will give you under the radical the square root. So perfect squares are the numbers, two numbers that are the same that you multiply together, all right? And it takes two to make a pair, so they represent a perfect square. So in the next video, I hope to explain the product rule of square roots. And then afterwards, we'll look at some other roots that are more than the value of 2, the index, and we'll do some examples for that. But this ends the series for right now. This is Irvin M. Howard, and thank you for looking at EMH Math Portal online instructional videos. You have a good day.